Clustering. We have now reached a part of the course where we're going to talk about unsupervised learning. In unsupervised learning, we let the data divide itself into different groups. So we let the data self-organize without the use of labels or other annotations. There's multiple reasons why you do not want to use labels in training. For instance, well, first of all, it's very expensive with labels themselves. It's relatively straightforward to collect more data. However, collecting annotations are often involving manual annotators overwatching or carefully walking through the examples and assigning a true or false label to the data. Another reason why self-organizing data makes sense is that, well, in supervised learning, we have lost the ability to do statistical testing after we have made our learning outcomes. And, well, at least without not using techniques like cross-validation, etc. However, in unsupervised learning, if we divide our data into different clusters, we could then just test if these clusters make sense compared to the labels. So we can even assign p-values, etc., to the outcomes of our experiments. In this course, we will cover two forms of unsupervised learning. First, clustering, that will be discussed in this lecture, and in a later lecture we'll talk about principal component analysis. A classical technique to cluster data is so-called k-means clustering. This is very well covered in this chapter of k-means clustering in your book. However, I will briefly cover it here as well. The process goes from just randomly selecting cluster centers, and then we repeat a couple of steps until we converge. Firstly, an E step where we assign points to the nearest cluster center, and then an M step where we set cluster centers to the mean of the points in the cluster. So say that you have given the two different features for a set of 12 different data points. Now, if we want to apply k-means clustering for this, we start off by just randomly distribute 3 different cluster centers. So here we have the cluster centers in blue, red, and green. So now we will sort of start our k-means clustering loop by firstly assigning each data point to a cluster mean. So you will select the cluster of the nearest cluster center. So anything that's close to the blue cross here, that will as well be assigned to the blue cluster. Anything close to red, or the closest points to the red marker, will be into red clusters, and the data points closest to the green will go to the green. This is followed now by a so-called M step, where the cluster centers to the mean of the clusters. So we just sort of take the feature values of all the data points in the green cluster and assign a new center based on this. The same is true for the other colors as well. This allows us to do a new E step, where we can assign new colors to our data points based on which center they're closest to. And note now that a couple of data points will switch color here, just depending on the cluster center have been moved from previous iteration. Once this is done, we can assign new cluster centers. And in fact, this is the cluster centers that will not bulge for next iteration, so then we have converged. In addition to k-means is so-called Gaussian mixture models. These are originally made for a different purpose. We often use these to estimate distributions or to trying to mimic different non-standard distributions, but this can be used for clustering as well. So the reason why this is somewhat more powerful than regular k-means clustering is that it allows us to weight the different features differently. K-means assume that there is sort of an equal distance between in feature 1 and feature 2. This is so-called circular or spherical distance matrices. However, we can allow us to include not just the different weight for different features, but we can as well model any covariation between the features. The book shows this quite convincingly, so I won't go into the details of this. Yet another nice feature with Gaussian mixture models are that there's an extension where we assign Dirichlet processes priors to the different clusters. This allows us actually to not having to select K. We can instead just select an upper bound for K. This tends to work quite well in cases that at least I'm experienced myself. Your notebooks will contain some example code using this for the case of breast cancer sampling. So please have a look on the breast cancer clustering web IPython notebook as well, and try to see how this works.